Okay. In the last lecture, we discussed about general characteristics of photodetectors. And we had listed first the quantum efficiency Q, quantum efficiency. Just to recall, the responsivity R, which is equal to the photocurrent generated divided by incident optical power P optical here, the response time or the rise time TR. So, rise time or equivalently response time or equivalently one can have discussion on the speed of response, and finally the dark current ID, dark current, or equivalently the noise power. So, these are the 4 general characteristics that we had listed in the last class, and we have seen that the quantum efficiency is basically the carrier flux generated, which means it is IP divided by E, carrier flux generated due to an incident photon flux, which is P optical divided by h nu. So, the power incident divided by energy of one photon gives you the photon flux, and this is the carrier flux, current is IP, and therefore divided by the charge gives you number of carriers or carrier flux. So, this we have discussed, and this we can write therefore as IP by P optical here into h nu goes to the numerator. So, we have h nu by E here. So, which is also equal to, this is the responsivity. So, this is responsivity R, this is equal to h c by E into lambda, 1 over lambda, and if we substitute this into, if we substitute lambda in microns, then this turns out to be 1.24. So, this is equal to R responsivity into 1.24 divided by lambda micrometer, just recalling, and therefore, we can write eta, the responsivity here, equal to eta into lambda divided by 1.24, where lambda is in micrometers. If we substitute lambda in micrometer, then the responsivity of a photodetector can be written in the form R is equal to eta into lambda divided by 1.24. where eta is the quantum efficiency of the detector, quantum efficiency of the material of the detector. In the last lecture, we have also discussed in detail how to maximize eta for a given structure and a given material, how one can maximize eta. And if we plot the responsivity therefore, so responsivity versus lambda, if we plot R here, then you would have straight lines for different values of eta. So, this is what we have plotted, eta is equal to 1, maybe 0.6, 0.3, and this is with wavelength. So, you can see the typical numbers when lambda is equal to 1.24. So, if you take lambda here as 1.24 and eta is equal to 1, then responsivity here must be 1. So, lambda is equal to 1.24, then responsivity will be equal to 1. So, this is the graph that we have for responsivity, assuming that eta is a constant. But in practice, eta is not a constant, because eta, if you plot eta, So, this is assuming that eta is constant, eta is the quantum efficiency, and if you plot eta for a typical detector eta versus lambda, the response would look like this. So, typically so this is for silicon and this is for indium gallium arsenide. Two very important detector materials, silicon and indium gallium arsenide, and the typical number, the responsivity of eta the quantum efficiency of silicon is approximately, the maximum value is about 0.9 and this is about 0.7, 0.8, and this occurs around lambda nearly equal to 0.8 micrometer. And this goes down to 0 around 1.1 micrometer here, and this goes down to 0 around 1.7 micrometer approximately. So, what I have plotted is lambda versus eta for typical detector materials, silicon and indium gallium arsenide. Now, why does the quantum efficiency go down at both the ends here? The longer wavelength end, it is obvious, because for a given material like silicon, silicon has a band gap Eg here. So, Eg is 1.1 electron volt. So, this is the conduction band and the valence band. Interband absorption, the absorption coefficient goes to almost 0 for energy less than the band gap. There cannot be electron hole pairs created, and therefore, the absorption coefficient goes down to 0. If you remember the graph for absorption coefficient, so if we have lambda like this, or photon energy, let me better plot in terms of photon energy. So, this is h nu. We recall that we have, so the absorption coefficient alpha here starts at Eg and then goes up. So, this is for silicon. So, this is Eg equal to 1.1 eV. So, h nu in eV, and this is alpha centimeter inverse. Recall the absorption coefficient as a function of photon energy. So, you can see that 1.1 eV is the band gap of silicon, and below which there is no absorption, and therefore, there is no generation of photocarriers by interband transitions, and therefore, the responsivity, the quantum efficiency of silicon goes down to 0 at longer wavelengths. So, there is a longer wavelength cutoff, exactly like that indium gallium arsenide has a cutoff around 1.7 micrometer, because indium gallium arsenide here, this is indium 0.53, gallium 0.47 arsenide. Why do we choose this combination? Because this combination is lattice matched to indium phosphide, so that we can grow defect free heterostructures. So, it is lattice matched to the binary compound indium phosphide. So, this has a band gap Eg of approximately 0.7 eV. So, you find that the long wavelength cutoff is here. So, we know why eta goes down to small values or goes down to 0 at longer wavelengths, because there is no absorption possible. Why does eta come down to 0 at shorter wavelengths? Energy is increasing, shorter wavelengths, absorption coefficient increasing, but why does it come down? There are two mechanisms due to which this comes down. So, let us discuss these two mechanisms. Very briefly and very quickly we will discuss. One, as energy increases, so first, because of generation of hot carriers, If you take the band gap here, so this is EK diagram, so K versus E, I have drawn an indirect band gap semiconductor to indicate that it is silicon, for example. And when the energy is larger, for example, this is the Eg, so this is Eg. For h nu, incident photon energy much greater than Eg, electron transition can take place, an electron can make an upward transition to an allowed state here. Electron from the valence band can make an upward transition due to absorption of the photon of energy h nu greater than Eg. It can make a transition to, because this is a vertical transition, which is an allowed transition, and therefore this carrier here is a hot carrier because it is a high energy carrier. So this carrier generated starts coming down by thermalization, the process called thermalization. We have discussed this earlier, and it comes down to the bottom of the band. In the process of thermalization, it gives down the difference in energy as phonons. So energy is given in terms of phonons. Therefore, generation of hot carriers lead to a large quantity of phonons in the lattice, and phonons present in the medium will facilitate non-radiative recombinations, very quick non-radiative recombination. In other words, the generated carriers will recombine very quickly by non-radiative recombinations. If the carriers are recombined very quickly, please recall we are discussing a photodetector here, material in which photons are incident, on which photons are incident, and it is generating electron hole pairs. So if you apply a bias, then electrons will move in this direction, holes will move in this direction, and the carriers are collected, and this is what is responsible for the reverse photocurrent IP. There is a photocurrent in the circuit. Now the generated carriers, if they recombine very quickly, then there is no more contribution to the current in the external circuit, and therefore the response of the detector goes down, or therefore the quantum efficiency of the detector goes down. Recall the definition of quantum efficiency as the carrier flux which contributes to the current in the external circuit, which means the carriers must be moving in the medium. If they recombine very quickly, then there are no more contributions to the external current, and therefore the quantum efficiency starts dropping. This is the first reason, generation of hot carriers. The second reason, so let me show here. The second reason is because of two, absorption near the surface, absorption near the surface. What do I mean by this? Let me explain again. I had the curve here, that is h nu versus alpha. As you can see, it is the same curve which I had drawn earlier. It starts from Eg. We are looking at lower wavelengths, response, that is quantum efficiency at lower wavelengths, and we are trying to explain why does it go down at higher energies or lower wavelengths. So higher energy here corresponds to larger values of alpha, absorption coefficient is very large, and therefore it means that the photons which are incident are absorbed completely close to the surface, because absorption is given by e to the power of minus alpha into d. D is the thickness over it where it is absorbed. Now if alpha is very large, then d needs to be very small. In other words, almost all the incident photon energy is absorbed close to the surface, and in any material, surface is not a very good place to get absorbed, because there are surface states due to dangling bonds in the medium, because near the surface, if you enlarge, we have discussed this earlier, but just to recall, if you enlarge the positions of atoms here and the bonds like this, you can see that to one side the bonds are dangling, they are free, they are not complete. and therefore, these dangling bonds, if you take the band gap, then they correspond to energy states somewhere in the gap. So, this is EV, this is EC, and this is the EG. Corresponding to the surface states, there are states which are in the forbidden gap, and these act like trap states, and they facilitate recombination of electrons and holes. So, again, just like in the previous case, the absorption near the surface, where there are plenty of surface states which act like traps in the medium, facilitate recombination of the carriers, quick facilitation of recombination of the carriers. If carriers recombine, means carriers are lost from the medium, which means they no more contribute to the current, and that is why the quantum efficiency drops down at smaller wavelengths. And therefore, the final picture now, the responsivity, therefore, let us very quickly come to the responsivity. If eta were 1, the responsivity would have varied like this, but eta varies like this, it is not 1, it varies like this, which means if I show you on the same plot, or let me show it separately, for a particular value of eta, let us say eta equal to 0.9. What I am plotting now is the responsivity versus lambda for real detectors with a quantum efficiency that is realistically varying like this. So, if I plot for silicon, as you can see 0.9 is the peak, and therefore, it will touch this around 0.8, other places it will drop down. So, it will go like this and then drop down. So, this where it touches is about 0.8 micrometer, 0.8 micrometer, and this is 1.1 micrometer, and this end is approximately 0.3 or 0.4 micrometer. So, what I have plotted is the real responsivity of silicon, varies like this. If you take a typical data sheet of any silicon detector, you will see the responsivity given like this. And if I want to plot for indium gallium arsenide, the maximum normally goes around 0.8. So, it starts from about 1 micron here, and this would go like this and come down somewhere here. So, this is approximately around 1 micron and goes up to 1.7 micrometer. So, 1.7 micrometer. So, this is for indium gallium arsenide. Responsivity versus wavelength. This is a very important curve because it tells you which detector to choose depending on the application. If you are interested in optical fiber communication, naturally you are in the 1.55 micrometer window here, and in gas is the best detector, and silicon will not work. But if you are interested in around 0.8, then silicon is the best detector. So, responsivity, this curve is very important in the choice of the detector. Okay. So, let us come to the third parameter, which is the speed of response or the rise time of the detector. The rise time of the detector determines the speed of response, how fast a detector is, and a discussion will tell us how the design engineer can go about in increasing the speed of the detector. What is the design, what is the structure and material one should choose so that the speed is very important. Okay. So, we consider, let me draw this diagram, redraw this diagram. So, here is the detector material, 2 electrodes deposited. This is the semiconductor material on which, let us say, a photon, one photon is incident. Let us first start with discussion of one photon incident at. So, this is, let this direction be x equal to 0 and the width of the detector is x is equal to w. So, this is incident at some value of x. So, this is some value of x and we have a supply which is connected to sweep the generated detectors. So, the incident photon gives rise to a hole and an electron and the applied potential will drift it. So, electron will move in this direction and hole moves in this direction and that leads to a current in the external circuit which is the IP photocurrent. Now, we are interested in knowing the speed of response or impulse response. Impulse response. Impulse response refers to response of the detector or response of a system to an input impulse. Impulse is an instantaneous pulse, impulse. So, instantaneous, so you have this system here. If you give an impulse, a signal with very small time duration impulse, how would the output look like? Whether this signal will spread. So, that will determine the impulse response of the medium. So, we have at an instant t, instantaneously one photon is incident at a particular instant. We want to see how would the current look like. So, photon is incident at one instant, how would the current in the external circuit look like. So, the current in the external circuit is given by Ramo's theorem. We are not going to prove this. So, Ramo's theorem states that the current I of in the external circuit is equal to minus if a charge q moves in a medium of length L or W, then I of t is equal to minus q divided by W into V of t, where V of t is the velocity, instantaneous velocity of the carrier, the charge carrier q. W is this width here and it is this velocity has come because you have applied a field. There is a drift velocity, as you know the velocity, drift velocity V is equal to mu into E, where E is the applied field, mu is mobility of the carriers. Mobility, mu is the mobility of the carriers, V is the drift velocity and E is the applied electric field. Therefore, we have a hole which is moving in this direction and an electron which is moving in this direction. Therefore, we have a hole current I h of t and I e of t. This is the current induced in the external circuit. So, there is a hole current and an electron current. So, electron current I e of t is equal to minus, charge is minus e into velocity of electron V e. If I take a average velocity, assuming that over the time duration the velocity is constant, so I can write V e divided by W. So, that is equal to E into V e by W. The electron is moving in this direction. So, the velocity is here. So, E V e by W. The hole current I h of t is equal to minus, charge of hole is plus E, but it is moving in the opposite direction. Therefore, it is moving with the velocity V h. I am writing a separate velocity because as we will see mu, the mobility is different for electrons and holes, and therefore, the velocity will be different although the applied electric field is the same, and therefore, V h divided by W, which is equal to E V h by W. The total current, therefore, the total current in the external circuit I of t is equal to I e of t plus I h of t, which is equal to E V E, so or E by W into V E plus V H. This is the current I of t in the circuit. The photo current is equal to E divided by W, this is E, a little bit bigger I have written, V E H. Is that all right? Okay. Now, if we plot this external, the current is the response of the detector due for the impulse. Impulse is the input photon or a burst of photons which are incident, and response is the current in the circuit. So, if I plot I of t, so with the time, so this is with the time, if I plot I of t, then I will get impulse response. So, impulse response is basically time spread over which the system is responding for an input impulse. So, let us first plot I e of t. Now, it would be worthwhile now to have some values of mobility, so that we have an idea in plotting. So, if you take material, let me give value for some materials. So, material mu e and mu h, mu e and mu h. So, if we take silicon, let me give you some numbers. So, this is 1500. What is the unit? Mu e and mu h, centimeter square per volt second, centimeter square per volt second. You can get from here. So, V is equal to mu into E. So, mu is equal to V by E. E is volt per centimeter and this is centimeter per second. So, you will get centimeter square by volt second. So, this is 1500 and this is 450. If you take germanium, this is 3900 and this is 1900. If you take gallium arsenide, some of the most widely used materials, gallium arsenide, you can see that this is 8500, whereas this is 400. The mobility of holes are much smaller. If you take indium phosphide, because gallium arsenide and indium phosphide are the most widely used binary compounds and these are the most widely used detector materials, 4600 and this is 150. And if we take indium gallium arsenide phosphide, indium gallium arsenide, the most important detector material, this is 14,000 and here 400. So, you can see the large difference between mobility of electrons and holes. This is now important because it will tell us what is the time taken by the detector. So, the current I e of t is equal to, so let me plot I e of t is equal to E by W into V E. And recall that V E is in general V E is equal to mu into E, electric field is the same, but mu E is large for electrons and this will be much larger compared to the whole current, because V H is smaller compared to V E. So, if I say that I e of t is equal to this value E into V E by W is somewhere here, then current will persist till the electron is collected by the electrode here. Electron moving in the semiconductor is responsible for a photocurrent. When the electron is collected, till this time current will persist in the external circuit. So, what is the time taken for electron to move from here to here? So, if this is W, then this separation is W minus X, this is X. So, this is X and this is W minus X. So, distance divided by, so T E is equal to W minus X divided by V. And there is the time taken. So, up to that time T e, the current will persist and then it will drop down to 0. So, this value here is T e is equal to W minus X divided by V. Now, the whole current we know is smaller because V h is smaller. So, let me start at some value here. So, this is, what is this value here? This is E V e by W. The value on the y axis here is E V e by W. The value here is W minus X by V e. We can put some numbers to get a better feel, we can always put some numbers. So, what kind of numbers are we talking of? I will discuss more about V e a little later, but typically V e is about 10 to the power of 6 or 10 to the power of 7 centimeters per second. W, let us say this is a 1 centimeter detector. There can be smaller detectors, but just let me put W approximately 1 centimeter to get a feel for the number, and E, as you know, is 1.6 into 10 to the power of minus 19 coulombs, and therefore, the current I is E, therefore 1.6 into 10 power minus 19 multiplied by V e 10 to the power of 7. So, this is coulombs, this is centimeter per second, and in the denominator 1 centimeter. So, this is equal to 1.6 into 10 power minus 12, that is picoampere. Why? Because we have put just one photon. The current is very, very small because one photon, there is one electron moving, and therefore, the current is very, very small. We will see how. So, just to get a feel, so that is the current which is persisting for a certain time. Again, you can put, say, this is about 1 centimeter, this 10 power 7 centimeter per second, therefore, the time is 10 power minus 7 second. So, approximately 0.1 microsecond, current persists for about 0.1 microsecond, all right. So, if you reduce this naturally, it will become a faster detector. So, you want to take a small area detector, we will discuss this later. Now, let us plot the whole current. So, it starts at a lower value, but it goes further. Why? Because where is TH? TH is equal to x, the distance x divided by VH. VH is much smaller compared to VE, therefore, so this is TH equal to x divided by VH. This is plot of I E of t, and this is plot of I H of t, assuming that the carriers are moving with a constant average velocity till they are collected at the ends. So, the total current will be the sum of the two. So, if I want to plot in the same sum of the two, so here it will add up. So, let me draw with the dotted dash line. So, my total current will look like this. The box with the dash line shows the total current. So, what I have plotted? I have drawn impulse response. At t is equal to 0, there was a photon incident on the detector. In the circuit, current persists for such a long time. So, the impulse response, as I showed, ideally I should have got the response current also for a very small duration, but instead the current is spreading over a long duration, and this is the impulse response due to one photon incident. Now, I will extend a little bit further to n photons, because we are interested in seeing n photons incident. So, the same detector now, but photons are incident everywhere, all over the detector, not at one point. If at one point there were n photons, then the current would have been simply multiplied by n. Same response will remain the same, but it will be multiplied by n. That is all, that is the only difference. So, this value here is I V e into W. If there were n photons incident at this spot, I would have got n e v by W. So, typically if a very small amount of a burst of n photons, let us say 1 billion photons are incident, then the current will increase by 1 billion times. So, this will become milliampere. All right. So, the numbers are quite practical numbers. Now, the photons are incident everywhere, not at one point, over the entire detector surface. What will happen? At every point electron hole pairs are generated, and electron which is generated here is instantaneously collected, whereas electron which is generated here will take a time t is equal to W divided by V is the total time. And so, if I plot I e of t, please see this. So, this is time versus I of t. So, first let me plot I e of t. So, it will be largest at t equal to 0 because all the electrons are moving, but the electrons which are generated here are collected. Once it is collected, no more contribution. So, the current will drop like this continuously till a time t. T is equal to, what is t? Will be equal to W divided by V e. So, this is T. The current is continuously, and what is the value here? N times E into V e divided by W, because there were n electron hole pairs created. Similarly, the hole current, holes which are generated here are immediately collected, but the hole which is generated here has to travel all along, and therefore, it will vary from a smaller value here. I am taking a smaller value. Why? Because the hole current is N E V h divided by W. V h is smaller than V e, therefore, it starts somewhere here, and then it will continue for a duration which is up to this. So, what is T h is equal to W divided by P h. What is the net? The net current is sum of these two. So, this plus this is here, and up to this value it will have a sum. So, you can and then it will go just over this. So, just to distinguish, let me draw these with the, this is the total current. So, what are the things I have plotted? I have plotted I h of t, I e of t, I e of t, and this is I total which is the photocurrent, I p of t which is equal to the sum of the two. So, the impulse, where was the impulse? Impulse is at t is equal to 0. At t is equal to 0, a burst of n photons were incident on the photodetector, an instantaneous impulse. The response is this. At the output, we see that the current which is the response of the photodetector is spread over a certain time. So, this is the impulse response. Now, what is our objective? If you want a high speed detector in an application, this should be as small as possible. If it was, so you had an impulse here, and then if you had got a response which is like this, then it would have been ideal, very fast. The detector is very fast. So, how can we get high speed? Obviously, you have to have as large, V should be as large as possible. First, T e should be equal to T h, otherwise this pedestal will always remain. So, if you can make T e equal to T h, how can we make that? It is possible that if this is the detector material, then you open a window somewhere here, then you see the electron will take a slightly longer time, whereas holes are very close to the not that that is very good, but I want to avoid the pedestal. This is the window where all the photons are incident. Then TE will also be slightly larger to match TH, so that this pedestal can be removed and we get a nice impulse response like this. First thing, we want TE equal to TH and as small as possible. How can we have as small as possible? W should be as small, which means you need a very small area detector. The detector should be very small, not a large detector which we use with the normal power meters. You have a large area detector, but all high speed detectors will have a very, very small area, because this is one reason. There is another reason, because smaller the area, smaller will be the junction capacitance, and the capacitance also determines the speed of response. But what we are looking right now is impulse response due to transit time considerations. We are looking at transit time considerations. So, this is impulse response looking at transit time. So, transit time consideration. The impulse response is determined by two factors. Oh, let me make this clear. The impulse response is determined by two factors. So, one, the transit time of carriers. So, transit time of carriers. So, what we have been discussing is the transit time spread. The second one, it is determined by the RC time constant in the circuit. There will be a detector circuit and there is an RC time constant in. This RC will include the RC of the detector itself. If I, for example, if I take the standard detector circuit, so here is, let us take a diode, pin diode here. So, this is the output, this is the RL, and here is plus 5 volt. We reverse bias it for getting a good drift current, drift velocity. Now, there is a load resistance and there is a junction, is a reverse bias diode. So, there is a junction capacitance. So, the speed of response tau or rise time is determined by the RC time constant, which is RL, plus if you write the equivalent circuit of the diode, there will be a series resistance and a junction capacitance. So, this will contain the series resistance and the junction capacitance C. So, this will determine, and the frequency, cutoff frequency of this detector will be 1 over 2 pi RL into C. So, the impulse response is determined by two factors. One is RC time constant. Therefore, if you take any photodetector data sheet, you will see they will specify the rise time, for a particular load resistance. You will normally they take 50 ohm as the standard load resistance. So, they will specify that tau is equal to 0.3 nanosecond at RL is equal to 50 ohm. That is the meaning, because the rise time is determined by the circuit, the load resistance and the junction capacitance, rather than the transit time. The transit time can be minimized. This factor can be minimized in semiconductor photodetectors by taking very small areas and very small length and very high velocity. So, this is the drift velocity. How does this is very interesting. How does this drift velocity vary with the applied electric field? We have some time. So, if you take VE very large and very small W, TE can be very small, and therefore, this transit time consideration, the impulse response is determined by two factors, transit time and RC time constant in the circuit, actual system circuit. This can be minimized so that it is primarily determined by this. This also, of course, one tries to minimize, but you cannot go beyond, because RL you have to put some load resistance. In a practical circuit you will see that if you reduce the load resistance, detecting becomes extremely difficult, but you can reduce to some extent, you cannot go beyond, but this can be really minimized. If you plot the drift velocity versus electric field volt per centimeter versus the drift velocity Vd of carriers. So, if I plot for electrons, so this is Ve, typically the velocities are, I will give some typical numbers, 10 power 5, 10 power 6, 10 power 7, 10 power 8, this is centimeters per second, and the field typical numbers are 10 power 3, 10 power 4 and 10 power 5 volt per centimeter. So, we can plot this, and typically this would look like, for indium gallium arsenide it looks something like this, greater than 10.7 and then drops something like this. Is for indium gallium arsenide highest. If you take germanium, it goes from here and then something like. If you take silicon, then so this is for silicon, this is for germanium, and this is for, I have already written, indium gallium arsenide. These are quite typical, the field is about 10 to the power of 3 or 10 power 4 volt per centimeter. It is volt per centimeter, but the typically we take thickness very small, less than a millimeter, and then the volts are, it is only few volts. You do not have to apply very large volt, it is volt per centimeter. Typically we take 0.1 mm or 0.2 mm as the dimension. So, this velocity here, the highest value or the saturated value, like you can see here it is saturated value, is designated as Vsat. So, what is the point? Point is you must apply an electric field so that you are already at Vsat. That is the maximum velocity possible. There is no point in applying very high fields nor low fields. So, when I have shown this plus 5 volt I have written, in some detectors you may need plus 15 volt, but I did not write 1 volt because that may not be sufficient, it may be here. Why they use plus 5 volt or plus 15 volt is to get a field which corresponds to Vsat, that is the saturated velocity. Now, where is the saturation coming? If you take a semiconductor, there are electrons and holes generated, electron moves, hole moves. When you apply a field, before you apply a field, nothing, it just does not move, there is nothing. So, that is why we had applied a field, right. So, you have applied a field here. So, if you have applied a voltage V and this is D, then you have E, electric field E is equal to V by D. So, there is an electric field which is applied. As you increase the voltage, electric field is increasing, the electron is getting drifted rapidly, but after some time when the electron is moving, it is also colliding with the atoms and electrons which are bound electrons in the lattice. So, it cannot go on increasing. After some time it has a saturated velocity, and that is the Vsat that we have. So, to summarize this impulse response, therefore, with these discussions what we have seen is impulse response can be made very narrow, or the speed of response can be very high, the speed can be very high if you operate with a velocity corresponding to the drift velocity, saturation velocity. If you apply an electric field corresponding to the saturation velocity and try to reduce the dimension of the detector, dimension of the active area. These are two from this point, and choose a material with a very large value of mobility. because velocity is equal to mu into E, and therefore, that is why we have been saying that this is the most important material and the most important material for optical communication, because the responsivity is the highest for this detector in the 1.55 micrometer window. So, this discussion tells us about the speed of response, and the last parameter is the dark current or the noise power. This we will discuss, if time permits, in a separate lecture, because noise power becomes very important when you have to detect very low power levels, and one has to choose a material which has very low dark currents. So, we will stop at this point. Is there any specific question?
So, when you say only one photon is falling on that surface, so there will be only one electron and one hole pair generated, right? So, how can the continuous current, it should be a spike only, right? We are collecting one electron.
Okay, the question is, this is the detector. So, the question is, one photon is incident, h nu, which creates one electron and a hole in the medium. Now, because of the applied field, they start moving, drifting to two sides, otherwise they would recombine again, because if there is no field, then they, so this starts, otherwise they would recombine again, because if there is no field, then they, so this starts VH here. As soon as the carrier starts moving in the medium, there is current in the circuit. It is not when it is collected you get current. Once it is collected, then it has gone into the conductor, no more current there. So, when it is moving inside the detector, then you have current, and because it takes certain duration, therefore, if you plot the current persists. I had taken one photon just to say that it will remain constant till it is collected and drop down. So, Ramos theorem shows, which can be proved actually by simple heuristic explanation, I of t is equal to minus q by w into v of t. So, the current persists over a certain time, so long as the charge is moving inside the semiconductor, and that is why there is a continuous current. It is not like a counter, when it has reached there is a count, there is a spike. It is not that, it is because of the motion of carrier there is a current, because current is basically flow of carriers. Is that okay? So, we will stop at this point.